In this example, we're going to do basically what we did in example number 2, but we're going to add a little bit of noise, specifically what we call white noise, to our data. Now, that's what that eta term means, is eta of 0, 0.02 means we're going to add normally distributed random numbers with a mean of 0 and a standard deviation of 0.02 to our original function. So I copied everything I had originally, and we can see that with no noise, what we have is exactly what we had before, obviously. But what I'm going to do is I want to add a little bit of noise to this, and I want to add it here. So rand n 0.02 times that, so that's going to have a mean of 0. It's going to have a standard deviation of 0.02 times the length of t1. Let's see what this does to our plot. And this is the wrong size. Okay, so now it should work. Alright, so now if we zoom in, see it's not perfectly smooth because it's not exactly e to the sine of x squared. There's that little bit of noise in it that's throwing it off, and this is more realistic of what we would see if we had some instrument that was collecting this data, is that it wouldn't collect it perfectly. It would have a little bit of this noise in it that's not going to give us a perfectly smooth signal. And if I run it again, since it's random, it's going to be a little bit different each time because of that random term that I'm adding here. And let me sample it more infrequently to start here. So every 1/10 of a second, we have a little bit of that noise there. So if I go and I do my 4th order differentiation again, with this little bit of noise, sampling it every 1/10 of a second, again, everything is the same as what I did before, we see that that noise throws off our estimate of the derivative quite a bit. So let me sample it a little bit faster, every 0.05 seconds. And we see that the plot, again, has a little bit of that noise to it at 0.05. Let me run the whole thing. And we see here that our derivative has a lot more of these changes here. And this goes to, in the presence of noise, the faster we sample, if we remain with the same accuracy, it actually can get more jumpy, I'll say, using that derivative. If we sample it even faster, we see that our estimate of the derivative is getting kind of worse and worse, or it's getting really jittery here from that little bit of noise that's being added to our actual signal. So this is a problem with real signals, is that taking the derivative can be actually somewhat difficult to do if you're using the raw data. As I've said before, it's kind of outside the scope of this class, but where this would go if you had real data that you wanted to differentiate, it wasn't perfectly formed from a function, probably the first thing you would want to do is filter it first, which would smooth out this noise in the original data, so then when we try to take the differentiation of it, then this is going to be better. Also, what we can do is take higher accuracy derivatives, and that can smooth it out a little bit as well. So maybe for this one, 4th order is not good enough if we're going to be sampling every 100th of a second. So again, filtering can help, and higher accuracy differentiations can help as well. Let's see what happens in contrast. So here I have my differentiation. I have the original. Let me actually add a 3rd spot here. So let's also look at the integral, what we did last time. So for this, I can use cum traps. And again, let me start sampling slower and see how this is affected. So my independent variable here is going to be t. My dependent variable is going to be y. And here I will plot in the 3rd spot my integral here, and then this will be the integral as well, so the integral of y dt. Right, so we see here I went back to sampling at 1/10 of a second. I have my original signal with that little bit of noise in it. I see dy dx is kind of choppy there for sampling infrequently, but my integral, using the Cume traps that we looked at last time, is fairly smooth. It's not really affected too much by that noise. If I go and I sample faster, so let me sample twice as fast. Again, original signal has that choppiness. Derivative is getting a little bit worse, but the integral is not really affected. It's still nice and smooth. If I sample even faster, integral still smooth, very choppy in my dy dx, and my y just has that noise in it. So, as I've been saying, the integral not really affected too much by that random white noise that we have, whereas the derivative is highly affected by the presence of noise there. So one lesson from this, if you are running a real experiment, depending on the type of equipment you have, if there's something you can measure easily and you need its integral, using numeric techniques you're probably better off than if you're measuring something and you need to be taking its derivative. So for example, if you're looking for something's velocity, and you have something that's going to measure its position, and you want to get its velocity from numerically differentiating, it's going to be highly susceptible to noise in that position signal. However, if you have a device like an accelerometer that's going to measure your acceleration pretty well, and then you want the velocity, you're much better off in that case integrating the acceleration to get the velocity. Then you would be differentiating your position to get your velocity because of the noise you're going to have in these real signals.